Good morning to everyone. I'm Lisa Canay, Chairman of Group C, and today I'd like to present you the steps and the outcomes for our third project of the Mechanical Vibration course, held by Professors Pellicano and Zippo, related to the study of car-induced vibrations on bridges. The goal of this project is to analyze a vibrating system consisting into a bridge, modeled as a simply supported beam, which is subjected to a constant amplitude load exercised by a running car. More specifically, we're interested in evaluating the value of using a DVA, comparing a case study where it is adopted with another in which it is not adopted. Briefly, I'm going to show you the workflow followed by me and my colleagues. Naturally, we began by looking for the information regarding the faced topic, doing some research and working on the theoretical development, the aim of which is to define the main features of the system and all the parameters required to define the Cauchy problem, and so laying the foundation for modeling in such a way as to implement it numerically with MATLAB, which in turn allowed us to find the natural frequencies, the mode shapes, and the transient response. After this, an interpretation and discussion about the results achieved led to drawing our conclusions. So let's start with the problem. As we can see in this slide, we've assumed a single-span bridge made of steel with double T cross-section beams, having a total length of 25 meters and 3 meters of width, subjected to a time-dependent force corresponding to the car and passenger's way, moving through the bridge with constant speed. The DVA is assumed to be in the exact middle of the bridge, as in this point the transient response will be analyzed. Besides, it represents a simple yet reasonable assumption, since it approximates nicely a real scenario. Indeed, some assumptions need to be made for studying a simplified problem. Particularly, the DVA is considered as a mass attached to a linear spring and damper that suspends it from a single point of the bridge, and the running car is taken as a constant and concentrated force. Moreover, to allow the replication of the analysis, we reported on the left all the parameters employed, deriving either from our researches or by assuming reasonable values. In the light of what has been described, the resulting equation of motion is shown here. As you can see, the system can be described by making use of the Euler beam theory. Particularly, we can easily distinguish the terms related to the elastic restitutional load and the inertial load, but you can also see the loads related to the DVA, followed by the expression of the external force. As you can imagine from the expression, 2 initial conditions and 4 boundary conditions will be needed to solve the problem. Most importantly, the geometry-related boundary conditions regard nil displacement and curvature in the extremes of the beam. Natural frequencies and the mode shapes have been our prime focus, as they are an important milestone to determine the vibrational behavior of the system. To analyze them, the bridge has been examined without the DVA and free from excitations. In addition, the structural damping of the beam is led to be zero. Admittedly, this will lead to the obtention of modal shapes and natural frequencies that are not proper of the real system, as the presence of the DVA and the structural damping will somehow alter these values. As a matter of fact, from our researches, numerous papers shows how to work around the effect of attachments, such as the DVA on a bridge, on the results of the Eigen problem in beam vibration, and we included also a reference to one by Pellicano if you're interested. Nonetheless, since we are talking about a civil engineering case, where the extra mass represented by the DVA is very small and so is the effect of the structural damping, these alterations will be extremely limited and will determine our approximation to be fully reasonable. As evidence of that, the same method has been used in the paper of Professors Pellicano and Somani about this same topic. Now, we can express the deflection of a given point of the bridge as the product of a space-dependent term and another one dependent on time, performing a variable separation, and by developing the expression, including the change of variable reported here, we can obtain a second-order differential equation with respect to time and a fourth-order differential equation with respect to space. Through development of the equation on the right, it is possible to demonstrate that a constant omega is a natural frequency, while with a further change of variables on the equation on the left part, we can achieve the expression of the mode shapes. To solve this equation, the aforementioned four boundary conditions are needed, and by solving the resulting algebraic system, we get the natural frequencies and the mode shape of the system. The solution suggests that the number of natural frequencies and therefore associated mode shapes are infinite. Focusing now on the transient response, by virtue of the superposition principle in terms of modal amplitudes, we can express the vibration of the beam considering the effect of each individual modal amplitude weighted by a term corresponding to the time history. This one is our first step to move from a partial differential equation to a system of ordinary differential equations by use of the Galerkin method. After superposition, we lean on the orthogonality properties of eigenfunctions and we merge these properties while applying modal projection in order to achieve a suitable form of ordinary differential equation describing the motion of the bridge. Focusing now on the dVA, the deflection of its spring and damper is equal to the difference between the deflection of the bridge at the point where the dVA is suspended and the motion of the mass. Applying again the superposition principle and considering the orthogonality conditions, we can obtain another ordinary differential equation describing the oscillatory motion of the dVA. As already mentioned, through modal projection, we obtain new forms of the elastic and inertial terms, and also the external force, which is now composed by a product of its amplitude times the auxiliary factor which replaces the Dirac delta times the Heaviside function that computes to 0 from the moment the car leaves the bridge. We finally add a term for the structural damping at each mode projection, and now we can write our ordinary differential equations for the motion of the bridge. But now let's explore what has been the outcomes of our mathematical development. Beginning with the natural frequencies and mode shapes, we can see clearly that results are consistent with what me and my colleagues expected. In fact, considering the first 6 modes of vibration, we ended up with a fundamental natural frequency of 12.09 radian per second, which is a quite reasonable value also comparing with other ones found. Of course, increasing the natural frequency, we can clearly see how the number of nodes increases as well as the number of peaks. For us, it's worthy to remark that the amplitude shown here in the graph is not representative of the real structure, instead it's just arbitrary. Furthermore, it is good to stress that taking as a reference the first 6 modes of vibration over the possible infinite brings to an incredibly small error committed, as in real structures, the very high frequency modes are unlikely to occur for the intrinsic characteristic of the system itself. Here we come to the main part of the project, the transient response. Considering that the red line represents the moment in which the car leaves the bridge, as we can see from the plot, the presence of a dVA brings the bridge back to stability much faster. Indeed, the transient response of the bridge without the dVA is really slow to reduce its oscillations amplitude, so much so that it seems as though the system were not even damped. After 100 seconds, it has not even halved the amplitude. Instead, the transient response of the bridge with the dVA expires very fast. Just 4 seconds after the car leaves the bridge, it has halved its amplitude, and after 60 seconds, it is completely back to the steady state. As a result, the fatigue life of the bridge is far longer with the dVA adoption, as the number of cycles undergone are much less. To highlight the hidden sides of the previous result, we believed that some zooms could help to make vivid some peculiar aspects. Most specifically, the structural damping presence is clear by the decreasing peak-to-peak amplitude of the bar beam response. Instead, from the right-hand side picture, we can see a second effect of the dVA, that is, the slight decrease in maximum deflection. Going on with our analysis, we have decided to take a look at the transient response of the system not only in the center of the bridge, but extend it to its full span, also with and without dVA, finding the behavior of both the beam and the DVA during and after the car's passage through the bridge. This dynamic animation shows that the presence of a DVA means the addition of a non-negligible mass. Despite its presence reducing the transient time and the initial amplitude after the car leaves the bridge, it also affects the response with an increased maximum deflection in the middle of the bridge under the passage of the car. Nonetheless, in order to show the real potential of the DVA, we run a final analysis using optimized value for the DVA taken from the paper by Professors Pellicano and Somani. And as we can see in this new plot and in its dynamic animation, the bridge turns back to its initial position with extremely low amplitude of oscillations, which translates into a drastic reduction of the amount of alternating stresses that the bridge is subjected to. In the end, there are several takeaways from this analysis. It is clear that the use of a DVA makes a huge difference, since it restores the initial state of the bridge very fast when compared to the bar bridge model, which has benefits both in terms of user comfort and fatigue life of the structure. However, proper design is crucial when considering this solution, as an incorrectly tuned DVA can be of little use or even detrimental. In order to properly tune a DVA, the rigidity of the spring and the damping, the suspended mass, and the location of the DVA in the bridge must be carefully decided following a multi-objective optimization process, where the designers are to pursue maximum energy dissipation with minimum deflection, and this means, of course, that a trade-off must be sought. Thanks you for the attention, and if there are questions, the group is more than pleased to answer your comments or emails.